So a number alpha, complex number alpha in C is called algebraic number provided it satisfies a polynomial with coefficients from Q, and it's a non-zero polynomial. We also have algebraic integer. Again, alpha in C is called an algebraic integer provided it satisfies a monic polynomial with integer coefficients. Satisfies monic polynomial with integer coefficients. So there is a polynomial, non-zero polynomial satisfied by an algebraic number, and what we shall see is that there is a monic irreducible polynomial satisfied by such an alpha algebraic number, and this polynomial is uniquely determined. So that is the theorem. Let alpha be an algebraic number. Then alpha satisfies a monic irreducible polynomial over Q. Alpha satisfies a monic irreducible polynomial over Q. This polynomial is uniquely determined. If this polynomial is Gx, and fx in Qx is any polynomial such that f of alpha equal to 0, then Gx divides fx. So this theorem says that given any algebraic number, we know that there is some polynomial over Q which is satisfied by this algebraic number, but moreover there is a monic polynomial which is irreducible, that is, it cannot be factorized into proper factors, which is satisfied by alpha, and this monic irreducible polynomial is uniquely determined, it is unique. And if there is any polynomial of which alpha is a root, then Gx divides fx. Proof of this: for the construction of this, we look at all polynomials having alpha as a root and take a polynomial of smallest degree. So let G1x be a polynomial over Q of smallest degree and having alpha as a root. It has some degree, means it is a non-zero polynomial. G1 may have some leading coefficient. Suppose C is the leading coefficient of G1, we divide by that. If C is the leading coefficient of G1x, define Gx equal to 1 upon C G1x. Then Gx is monic and G of alpha equal to 0. Gx is a polynomial over Q and G of alpha is 0. Now we want to show that Gx is irreducible. So suppose, if possible, Gx is reducible. Okay? That is, it is not irreducible. Irreducible means you cannot factorize it as a product of polynomials of positive degree. If it is reducible, we can write Gx equal to a product of two polynomials. Let us write it as G1x, G2x with degree of Gix bigger equal 1. Each Gix, G1x and G2x has degree bigger equal 1. It also means that sum of the degrees of these two is equal to the degree of G. So each has degree smaller than that of small g. Therefore each Gix has degree less than degree of Gx. Now G of alpha equal to 0, so G1 alpha, G2 alpha equal to 0, and so either this is 0 or this is 0. Therefore G1 alpha equal to 0 or G2 alpha equal to 0. So we have got a polynomial of degree smaller than that of G. That's a contradiction because Gx was a polynomial of smallest degree having alpha as a root. This is a contradiction. As degree of Gix is less than degree of Gx. That shows that Gx is irreducible. Hence Gx is irreducible. Suppose we have another polynomial, say capital Gx, which is also monic and irreducible. So let Gx be a monic irreducible polynomial satisfied by alpha. Now divide Gx by small gx. Now you get some quotient and get some remainder. Write Gx equal to small gx into qx plus rx with rx equal to 0 or degree of Rx less than degree of Gx. Now, G of alpha equal to small g alpha q alpha plus r alpha. Here this is 0, capital G alpha is 0 and small g alpha is also 0. Therefore, r alpha equal to 0. If Rx is not equal to 0, we get a polynomial of degree less than degree of Gx and satisfied by alpha. Rx itself is a polynomial of degree smaller than degree of Gx and it is satisfied by alpha. Now this is a contradiction because G was of smallest degree and Gx was satisfied by alpha. Therefore, R of x is 0. It is the 0 polynomial. Therefore, Gx equal to small gx into qx. Now, Gx is irreducible. That is given to us, and now you see some factors of this. But you cannot have factors like this of degree bigger than 1 because capital Gx is irreducible. So if you see some factors, then at least one factor must be a constant. Okay. But Gx is non-constant. Since Gx is non-constant, Qx must be constant. that is of degree 0. This is because Gx is irreducible. Now what is this constant? Since both Gx and small gx are monic. See that capital G is monic and small g is monic, and this is a constant. So if you compare the leading coefficients, then we see that this Qx must be equal to 1. We get comparing leading coefficients that Qx equal to 1, Qx equal to 1, and that is capital Gx equal to small gx. This shows that there is a unique monic irreducible polynomial satisfied by alpha. Thus, there is unique monic irreducible polynomial satisfied by alpha. From what we have proved, we also see that it is a polynomial of smallest degree with leading coefficient 1. That is how we have constructed it. From the proof, we see that it is the polynomial of smallest degree satisfied by alpha and with leading coefficient one. Leading coefficient 1, that is, it's a monic polynomial. The last part of the theorem is to show that if there is any other polynomial having alpha as a root, then Gx divides fx. Let fx in Qx be such that f of alpha equal to 0. Again use division algorithm. Fx equal to Gx into some polynomial Qx plus Rx with Rx equal to 0 or degree of Rx less than degree of Gx. Putting x equal to alpha, we get R alpha equal to 0 since Gx is a polynomial of smallest degree satisfied by alpha. We see that this Rx must be 0 polynomial. If Rx not equal to 0, we get a contradiction to the fact that Gx is of least degree and satisfied by alpha. Because degree of Rx is smaller than degree of Gx if Rx is non-zero, and therefore Rx must be 0. That is, Gx divides Fx. That proves the theorem. So, here we have shown in this theorem that given any algebraic number, there is a monic irreducible polynomial satisfied by this algebraic number. This polynomial is uniquely determined and it is called as the minimal polynomial of the algebraic number. And similarly, if you take the corresponding equation Gx equal to 0, G is the minimal polynomial, Gx equal to 0, this equation is called minimal equation of the algebraic number. Let alpha be an algebraic number the unique monic irreducible polynomial satisfied by alpha, say Gx, is called the minimal polynomial of alpha. It is the monic polynomial of smallest degree satisfied by alpha. The equation Gx equal to 0 is called the minimal equation of alpha. The minimal equation of alpha. It is the equation of smallest degree. It's monic. Now, this Gx is uniquely determined and its degree is called as the degree of the algebraic number alpha. The degree of Gx is called the degree of the algebraic number example, if you take alpha equal to cube root of 5, this is an algebraic number, in fact algebraic integer. Alpha is an algebraic number, in fact an algebraic integer. Why? Just look at its polynomial. Alpha satisfies gx equal to 0, where what is gx? Alpha cube equal to 5. So x cube minus 5, that is gx. Gx equal to x cube minus 5. Now, is this the minimal polynomial of alpha? So this is monic, gx is monic. Now, is this irreducible? That's the question. If this is irreducible, this is the minimal polynomial of alpha. Now, there are two ways of showing that it is an irreducible polynomial. One thing is that if you know the Eisenstein's criterion of irreducibility of a polynomial, using that you can show that this is irreducible. The criterion will tell you, because 5 is a prime number and 5 does not divide the leading coefficient, but 5 divides all other coefficients. 0 into x square, 0 into x minus 5. The coefficients are 0, 0, minus 5. So 5 divides all the coefficients other than the leading coefficient, and 5 square does not divide the constant term. 5 divides the constant term, but 5 square does not divide the constant term. That shows that the polynomial is irreducible. Another way of doing that is that this polynomial is of degree 3. If it is reducible, then what can you say about the factors? So if you write g as g1 into g2, then one of the factors, proper factors if there are, one of the factors is of degree 1 and other is of degree 2. Now, this degree 1 factor, what are its properties? So, if gx is reducible, we can write gx equal to g1x into g2x. One of them is of degree 1, other of degree 2. Is of degree 1 and other of degree 2. Now, we can assume that these polynomials are monic. We can assume that g1x, g2x are monic. Because you can take the coefficient of the highest degree term in g1. If it is c, you can divide this by c and multiply this by c. Okay, so the leading terms get adjusted and we can make both of them as monic. Gx is monic already. And G1x is of degree 1, suppose, and G2 of degree 2, suppose. G1x is of degree 1 and G2x of degree 2. Now, the theorem of Gauss says that if you take a monic polynomial with integer coefficients and write it as a product of two polynomials G1 and G2 over Q, this factorization is over Q, remember, that we can write this Gx equal to G1x into G2x, where Gix belong to Qx. Okay. Moreover, you can make them monic, that's what we have mentioned here. So, when we have a factorization like this of a monic polynomial over integers and this factorization is over Q, these factors G1 and G2 must be polynomials over Z. Okay. So, here G1, G2 are in Qx, they are monic, and Gx itself is monic with integer coefficients. Since Gx is monic and in Zx, okay, because Gx is x cube minus 5. So, this is a polynomial over Zx, it is monic, and G1x, G2x are monic over Q. They are monic polynomials and over Q. What do you get? By Gauss theorem, G1x, G2x are in Zx. If G1x equal to x minus a in Z, then by comparing coefficients, so G is equal to G1 into G2. So, this A into something is equal to 5. Okay. So, A divides 5. Therefore, what is A? A is an integer, so it is plus minus 1 plus minus 5. Here A is a root of G1x, therefore A is a root of Gx. Since A is the root of G1x, A is the root of Gx. And that's not possible. That A is plus minus 1 plus minus 5. None of 1 minus 1, 5 minus 5 is a root of x cube minus 5, x cube minus 5. They are not zeros of this polynomial. That means the polynomial is irreducible. If you suppose it is reducible, then one of the factors must be linear. If that factor is linear, moreover we make it a polynomial over integers. G1 and G2 both are over integers by Gauss theorem. So you can have G1x as x minus a, and that a must be a divisor of 5. A is an integer, so it must be plus minus 1 plus minus 5, and a does not satisfy the original polynomial gx. That shows that you cannot have a factorization like this. So such a test is possible whenever the polynomial is a cubic polynomial or a quadratic polynomial. If you want to show that a specific monic polynomial over Z of degree 2 or 3 is irreducible, then one of these methods is that just like this you write Gx as G1 into G2. One of the factors is a linear factor, degree 1 factor. Then you can assume that G1 and G2 are both monic. By Gauss theorem they are over integers, and then if the linear polynomial is x minus a, that a has to divide the constant term. Then just check whether it is a root or not. This is the usual test, and getting linear factors we use such a test. Okay. So that shows that this is irreducible. In Qx. This cannot be factorized over Qx, over Q. Therefore, cube root of 5 is of degree 3. It's an algebraic number of degree 3. Now we will see a test for an algebraic number or an algebraic integer. So suppose we have theta 1, theta 2, theta n as complex numbers, and you are given some complex number theta which satisfies the following properties. That consider theta into theta 1. This you can write as a combination of theta 1, theta 2, theta n with rational coefficients. Similarly, theta times theta 2 also you can write as a combination of theta 1, theta 2, theta n with rational coefficients, and likewise you can do it for theta into theta 3 etc. up to theta into theta n. If you can do this, then you can show that theta is an algebraic number. So theorem, let theta 1, theta 2, theta n belong to C, and suppose theta belongs to C satisfying the following relations. Theta into theta 1 is equal to a11 theta 1 plus a12 theta 2 plus a1n theta n. Similarly, you can write for theta into theta 2 etc. theta into theta n a n1 theta 1 plus a n2 theta 2 plus and so on plus a n theta n with aij as rational numbers. Then theta is an algebraic number. Aij are rational numbers for all I and j. Then theta is an algebraic number. Whereas if aij are integers, then theta will be an algebraic integer. If aij belongs to z for all ij, in the set 1 to n, then theta is an algebraic integer. This is proof is given by linear algebra proof. So what we do is we write everything on the left hand side. So theta 1 is here, theta 1 minus a11 theta 1. So we can write it as theta minus a11 into theta 1 plus something into theta 2 plus something into theta n. And we can write some equations like this. From given we have theta minus a11 theta 1 minus a12 theta 2 minus etc. minus a1n theta n equal to 0. Similarly, second equation you can get minus a21 theta 1 plus theta minus a22 theta 2 minus etc. minus a2n theta n equal to 0. Here you have theta minus a22 and all others are minus a21, minus a23 and so on. Continuing like this, we get minus a n1 theta 1 minus a n2 theta 2 minus etc. Finally, plus theta minus a n n theta n equal to 0. Here we are assuming that theta 1, theta 2, theta n are complex numbers and we assume that they are not all 0. At least one of them is non-zero. So now let me make this condition here that not all 0 in the statement of the theorem, that theta 1, theta 2, theta n are not all 0. That is what we shall use now. This can be considered as a system of homogeneous equations these are n homogeneous equations and having a solution theta 1, theta 2, theta n. This theta minus a11 minus a12 etc. can be considered as coefficients, and this can be considered as a system of homogeneous equations. There is nothing on the right hand side, constants are 0 with a non-zero solution theta 1, theta 2, theta n, because at least one of the theta I is non-zero. That is the assumption in the theorem. Therefore, the determinant of coefficients must be 0. Therefore, this is by linear algebra. That is determinant theta minus a11 minus a12 etc. minus a1n, then minus a21 theta minus a22 etc. minus a2n, and finally minus an1 minus an2 etc. theta minus ann determinant is equal to 0. Now, if you expand this, we get product of these gives rise to theta raised to n, and then there are other terms in theta. So, theta raised to n minus 1, theta raised to n minus 2 and so on, theta and constant. So, this is a polynomial in theta of degree n, it is a monic polynomial and its coefficients are over rationals. This gives us a monic polynomial in theta of degree n and with rational coefficients. So, this polynomial is satisfied by theta, and it means that theta is an algebraic number. Therefore, theta is an algebraic number. Now, if these elements Aij which appear here, that is theta 1 is a combination of theta 1, theta 2, theta n with integer coefficients. So, all Aij are even or integers, we assume that. In that case, theta will be algebraic integer. So, if all Aij are integers, then theta satisfies a monic polynomial. Here the word monic is important, with integer coefficients. And what does this mean? That means theta is an algebraic integer. Therefore, theta is an algebraic integer. This is a very useful criterion for theta to be an algebraic number or algebraic integer, that we should be able to find theta 1, theta 2, theta n, which are complex numbers, such that each theta theta I is a combination of theta 1, theta 2, theta n with rational coefficients. If you can find such theta I, then it would mean that theta will be an algebraic number or algebraic integer, depending upon whether these Aij are rational or integral. So now we will use it and show that some difference product of algebraic numbers is an algebraic number. Some difference product of algebraic integers is again an algebraic integer. So the next theorem says, if alpha beta are algebraic numbers, then so are alpha plus beta and alpha beta. If alpha beta are algebraic integers, then so are alpha plus beta and alpha beta. In fact, the proof will also show that if degree of alpha is m and degree of beta is n, then alpha plus beta and alpha beta, they satisfy a polynomial of degree mn. That can be shown. So let me also do some simple results about minus of alpha and 1 upon alpha in the case when alpha is an algebraic number. So let me do that first. So this is a simple result I will do first. Theorem: if alpha is an algebraic number, so is minus alpha, and 1 alpha is an algebraic number if alpha is not equal to 0. And in the same way you will be able to get if alpha is an algebraic integer, so is minus alpha. Negative of an algebraic integer is an algebraic integer. So the proof is you just take some polynomial satisfied by alpha. So proof, suppose alpha satisfies fx equal to 0, where fx is of the form x raised to n plus a1 x raised to n minus 1 plus and so on plus an, ai belong to Q. Now consider f1x equal to, see, replace essentially x by minus x and change sign if required. So you get the polynomial x raised to n minus a1 x raised to n minus 1 plus and so on plus minus 1 raised to n into an. Consider this polynomial. Now in this, if you put x equal to minus alpha, then f1 of minus alpha will be, it is minus alpha raised to n, and every time you will get minus 1 raised to n into f of alpha. Just check this, that here minus 1 raised to n minus 1 and alpha raised to n minus 1, and that minus sign is there. So minus 1 raised to n, so that is 0. That shows that minus alpha is an algebraic number. And so in the same way you can get, if x is, so alpha is algebraic integer, then so is minus alpha. If alpha is algebraic integer, so is minus alpha by the same argument. And finally, you just replace x by 1 by x in that and multiply by x raised to n. Clearly, 1 upon alpha satisfies 1 plus a1x plus etc. plus an x raised to n equal to 0, where ai are rational, and therefore 1 by alpha is an algebraic number for alpha not equal to 0. Okay, we stop here.